All right, and so at this point, I believe anyone viewing this video lecture here is ready for another class, another type of improper integral right here. But so at this point, I don't want anyone to worry about improper integral, but let's look at another integral right here. But it could be a little dangerous. Okay, so let me introduce the following problem right here, and then we will realize its specialty as well as how it could be a little dangerous a little bit. Okay, so let's look at and I'm not going to rush into introducing what type of integral that is, what type of improper integral that is, and you don't even need to worry about whether it's an improper integral or not. So let's just simply think about for anybody that when you're in that situation that you are given an integral. So here I have an integral from, how about from, on the function 1 over x, and it's a definite integral, from 0 to 1. Right from first sight, and only looking by judging by first sight, only judging the problem like this simply by first sight. That's what I mean right here. Could be dangerous. Okay, it looks right by first sight right here. It looks so much like a definite integral, an ordinary definite integral. What about another one? How about an integral? Well, same function, 1 over x. But how about an integral from -1 to 0? Okay, or it could be another one. How about tangent of x? Okay, but from 0 to pi over 2. Okay, so any of these problems I brought up, and so here let me show you. Any of those problems I had on the other board is a little dangerous in the sense that, again, right from first sight, right by judging from first sight right here, then any of them looks just like an ordinary or just a standard definite integral. So you would naturally think like this way: 1 over x, taking the definite integral from 0 to 1. Let me start out with that one right here, and I'm writing that here on the board again. So fundamental theorem of calculus says we are going to first find the antiderivative. That gives me natural log of absolute value x. And then further, we're going to follow further with the fundamental theorem of calculus, which states that we can now evaluate this antiderivative at 0 to 1. Okay, and then we are going to substitute these two values, but this is where a red critical line is going to start blinking right here, because, well, if we're substituting 1 into natural log of x, that is entirely okay. Natural log of 1 minus natural log. Now think of what would happen if we are substituting in 0 for natural log of x. I mean, substituting in 0 for x, and so consequently we're ending up with natural log of x. But this is where, you know, if this is when it runs into a problem like this, then usually if we're on a computer, then the computer is going to mark that as a red critical incorrect work right there, because now if you look a little more closely, it is impossible to find logarithm of a 0. 0 is not in the domain for the logarithm function. Okay, and so we can't. Obviously, I pointed out that we can't go this route now, because the lower end on this integral limit. So now back to the problem, we actually realize even further that we left out a little details. We loved the fundamental theorem of calculus so much that we just tried to find every single chance that we can get into using it. But then at some point we will naturally forget to and may skip a couple of details that could become a danger right here. This lower end of our integral, of our definite integral. Now, the fundamental theorem of calculus stated clearly that in order for the fundamental theorem of calculus to work, the function, this is the function, f of x, the function must be, so when I introduced the fundamental theorem of calculus itself, myself, I did not focus too much on that because I want people to start enjoying it fast. But now I have to emphasize, in order for the fundamental theorem of calculus to work well, then the function it's quite critical with that requirement. The function must be it's not only is, but it must be continuous. Now, continuous in what? Continuous in at least the interval, now from the low end to the high end, meaning it has to be continuous, including at 0 and all the way in that interval up until x equals 1. So this function is continuous at 1, that's good, and it's continuous anywhere between 0 and 1, but sadly this function 1 over x, anyone arriving at a at a calculus course should be well aware that 1 over x is discontinuous at x equals 0. So in other words, our function here fails that big requirements in order for us to apply the fundamental theorem of calculus. Okay, so it's another one. So now we're looking at, so this is the reason why this problem all of a sudden becomes dangerous, in the sense that it looks so like any definite integral out there, but we cannot proceed in the usual way with the fundamental theorem of calculus. All due to that reason, it has a discontinuity. Here in this case specifically, it's discontinuity. The function is discontinuous at the lower limit. It fails this requirement. The function in our integral problem fails that requirement about being continuous on the left end of the integral, on the left end of the integration interval. Okay, and so let's look at another one. So what about that one right here? Same function. So now you can see that, and now I don't have to. You start picking up from in the way where I'm going. So now I'm gonna just simply pointing it out. You see, I brought up the idea about discontinuity. So now think about that. This function, this interval, making the integral looks just like a definite integral, any ordinary one out there. And then we can quickly check that the function here is continuous at x equals -1. The function is continuous in any value between -1 and 0. But now sadly, the function is not continuous or discontinuous. It's not continuous at x equals 0, which is the upper end of our integral right there. So we can't so going in that route. So after making that note, allow me to erase that. So we can't go in that route by saying, hey, take the antiderivative, sweet, we found a solution, and then substitute in -1 and substitute in 0, because even when we arrive at that antiderivative, we cannot substitute that 0 into the logarithm function. Okay, because the logarithm function does not have x equals 0 as part of its domain. Okay, so anyone at this point, now I brought in that concept about continuity and discontinuity, so it is important that you review your calculus 1, your differential calculus understanding, because that's where I specifically taught about continuity and discontinuity back there. And then you got it also, and here I talked about the domain right there and all that idea about the domain of logarithm. Review your skill in logarithm from any of your algebra courses prior to calculus. Okay, so again, this is another example where the definite integral looks just, the integral looks just like any ordinary definite integral, but we will definitely fail to use the fundamental theorem of calculus to work it through, because we have to, because you see, if you're using that, then we're going to run into some discontinuity. We can't substitute the values in. In this problem particularly, and then the upper case, the upper limits of our integral is the discontinuity one. We need, according to the fundamental theorem of calculus, we need that requirement that the function is continuous in the whole interval from -1 to 0. But here we have from the interval from -1 to 0, we fail continuity right there. Okay, that's why I put that big cross there. Okay, so what about this tangent right here? So now once you start building even a little more experience, now we look over to tangent of x, this integral on the tangent of x. Again, gosh, it looks just like any of those ordinary definite integral. But now sadly, tangent of x, well, tangent of x is continuous anywhere between these two values from 0 to pi over 2. Tangent of x is continuous at x equals 0. Review your understanding in trigonometry. But sadly, tangent of x is discontinuous right at right at x equals pi over 2, simply because tangent is famously defined. Tangent of x is famously defined as sine of x over cosine of x. So when we're looking at x equals pi over 2 right there, then cosine of pi over 2 will give us a 0. And so in that way, tangent consequently is undefined at x equals pi over 2. So we have another discontinuity right there for tangent of x. And so this is why, so now in the end, my point altogether is that we are now working with the kind of, so we realize that none of these can be simply regarded as an ordinary definite integral. But so now we start turning our focus to, hey, so these must be some kind of improper integrals, okay? Unlike the improper integrals we have learned earlier, where the interval is an infinite interval. So here in these integrals, the interval looks like a definite interval, but it has discontinuity. So in this interval of integration, the low end of the integral limit is a discontinuity. Okay, discontinuous or discontinuity. We have a discontinuity right here, and we have a discontinuity right at x equals. All right, so those are, so we're going to have some discontinuity in our integration interval right here. And these are not all of the improper integrals form that involves a discontinuity in the interval yet, but at least these are the two fundamentals, one that built the other improper integrals that has discontinuity in their interval of integration. Okay, and so now I introduce for anyone viewing this video the first two forms right here of this another class of improper integral, the improper integral, the kind of improper integral where you have a discontinuity somewhere in your interval of integration. But then here specifically I would like to focus in the case where first the discontinuity is happening at the lower limits of your integral interval, or the discontinuity is happening at the upper limits of your integral interval. Okay, and so now I'm going to start erasing the board here and going to come up with a plan right here. So just similar to very similar planning with how I was doing that with the infinite interval improper integral. Then I'm going to show some planning, work out a couple steps, and then we're going to handle the problem. And then we are going to start getting into a formal definition of this type of improper integral. Okay, so now let's look at that 1 over x right here function. Okay, and the first one I brought up was from 0 to 1. So I pointed it out clear that we had a discontinuity right here. Okay, discontinuity at x equals 0. Okay, so now let me bring that up on the graph right here. All right, so here we are on this graphing space. And allow me to show the graph of our famous function 1 over x. Okay, so here's our graph for 1 over x. All right, so here we are, 1 over x. So the interval that we're looking at, so think about this. Now, don't worry about this other line right here, but I want you to focus on this portion right here because we're going from 0 to 1. So the interval is from 0 to 1. Okay, so 1 is the function itself is defined at x equals 1. Okay, and I hid away the numerical label right here, but this is x equals 1 and x equals 0 is right here. But we are well aware that this function 1 over x is asymptotic as x is getting closer to x equals 0. And so you can see that no matter how far I drag it up, no matter how far I I zoom out, you can see that the function will keep getting closer and closer to the y-axis, but will never cross through to go to the other side. And that's, you know, the property, the algebraic property of these 1 over x function, this specific function 1 over x. And so now, let me now describe the situation. So if we can't substitute in, as I have expressed on the board earlier, if we can't substitute in x equals 0 because the function is discontinuous, then so here's the plan. Why don't we create an arbitrary t value, anywhere less than 1, okay, anywhere. So 1 is here, and you can see that I just now drag a handle out, but I didn't go all the way to t equals 0. I just stay somewhere between 0 and 1. So my t value here is just some arbitrary finite value. I have to be clear. So t value, arbitrary t value, but finite, but less than 1. Okay, and so that's the beginning of the plan right now. So for this one right here, to work around with that, the 0 discontinuity right here, I'm going to think about, hey, why don't we create an interval? I mean, create a really usual definite interval from t to 1. Okay, from t to 1. On this same function, 1 over x dx. Okay, that's what the accumulation on the graph we've had earlier is for. All right, from t to 1 on the same function 1 over x. So this accumulation has generated an area in blue for us right there. And so now, but this is in the end, t will never be equal to 0. And I have to make a note right here. T is, of course, greater than or equal to, less than or equal to, actually strictly less than 1. Okay, so t needs to be a value anywhere strictly less than 1. That's a requirement. But you can see that we don't want t to equal 0. So yes, it makes sense, greater than 0 as well. Okay, so now with this t being arbitrary, we have for ourselves an arbitrary definite interval as usual. Okay, but so the work here will be natural log of x, and here at least now I can guarantee for myself that the function 1 over x will be definitely continuous anywhere from t to 1 in this integration interval right here. So we can go ahead and do the antiderivative thingy, and then substituting in from t to 1 right here, and come up for ourselves according to the antiderivative. I mean, according to the fundamental theorem of calculus. It's going to go natural log of 1 minus natural log of t. Okay? But in the end, this answer is not the answer for that, because this is from 0 to 1. Okay? And you can think about that. If I choose a t, let's say t here can be a 0.5. But that interval from 0.5 to 1, on my graph right here, 0.5 is about here. If we arbitrarily choose t to be 0.5 and the shading from 5 to 1 is some area, but now of course it's being less the area compared with the shading, with the accumulation from 0.25 to 1, or from even 0.05 to 1. Okay, and I'm not even sure if I'm on the proper scaling anymore, but any of these arbitrary t being less than 1, so you can now sense that the further we drag this handle further and getting closer to 0 right here, then we get more area. And then it seems like, according to the picture, then as we keep dragging that handle out and getting further to trying to head out to x equals 0 right there, then we will reach to tentatively that accumulation, that supposedly the accumulation all the way from 0 to 1 right there. All right, and so that action of mine where I was dragging that handle to move it, to head out to x equals 0, that is indeed the operation where I'm letting t, it's a limits problem. Okay, that dragging work, I'm trying to demonstrate the idea that we're doing the limits operation. But this time I'm taking limits as t is getting close to 0. T is getting close to 0. We saw all that on the graph. T is getting to 0. But then we got to be more precise than that. T is not only just getting to 0, but it's getting to 0. See, 0 is here at that destination, and t is getting to 0, but any of our t value is from the right-hand side of 0. So now what I mean here is precisely and specifically, we're defining that operation where I mean, we're creating that work where we have to now, to achieve that actual area, that accumulated area, we have to approach t to 0 from the right hand side. Okay, so that's what that's what the superscript plus sign here is for. So that means this limit operation is supposed to be carried along any of our fundamental theorem of calculus steps right here. So limit as t approaches 0 from the right hand side, and here I also need to take a limit as t approaches 0. So that's the plan how we handle this specific problem. And so the work here, the belief here is that as t really hits to that destination, I mean, for the limit to work, we will never be at t equals 0. That's the idea, but we keep getting t closer and closer to 0. And so hopefully we will achieve, and you have seen this all over in your differential calculus days, that as a variable getting close to 0, it all depends on the problem. We got all kinds of fascinating things out there. So we hope that we're going to have some definite numerical answer as the outcome for this calculation. Okay? And so now with this one right here, logarithm of 1 is 0. Okay? But it means we take natural log of t, that's a function, and we take the limits operation as t getting close to 0 from the right hand side on this function minus natural log of t. Okay? And so, well, taking antiderivative produce for us natural log of absolute value t, so as t is getting close to 0, then recall from yourself about the natural log. Natural log function as we get close, and let me quickly put the graph of natural log here. And for anyone in learning about integral calculus, now I have all my reason to expect that you know at least the basic graph for all of these functions right here. The logarithm, the exponential, the polynomials, and all that. Okay, logarithm looks like that. So as we get closer, as t or the x-axis gets closer to 0, then your vertical value keep dropping infinitely negative. Okay, and so now that means now for this limit, unfortunately, we reach down to minus infinity. Okay, so we kind of get some answers. So the idea now I can see is that the only way to handle an improper integral like this is, first, I'm not saying that they are equal, and we will get more precise into that, but the first thing is, as a plan, as the beginning of the plan, we have to create, instead of getting directly into doing any calculation, we have to create a limits problem on an arbitrary definite integral from an arbitrary t variable to 1, or to the other side of the integral. And then here in this case, since our lower end is the arbitrary one, we have to let that approach our desired value. Our desired value here, I'm going to let t approach that desired value from the right hand side. Okay, so similarly, and of course I'm not going to get straight into discussing what that final answer of this is yet. Allow me to get closer to that, get more precise on that later on. But now, just like that, the other one that we have seen. Okay, let's look at what about a negative 1 to 0 for 1 over x dx. Okay, so this one right here, let's look at the plan again. So we know that our function is discontinuous right at x equals 0 right here. So here's the plan. Why don't we create a t value anywhere greater than negative 1? Okay, just like similar to our work earlier. But now I put that t as an arbitrary value to be my upper limit of the integral problem like that. Okay, so now at least, now if t is an arbitrary value but strictly not 0, t is not 0 and then arbitrarily greater than negative 1, then here this is an entirely fine looking definite integral where we can go with the fundamental theorem of calculus. So natural log of x, natural log of x, and then we're going to substitute in minus 1 to t, and then it's going to become natural log of t minus natural log of absolute value of negative 1. Keep in mind that anytime we're taking antiderivative of 1 over x, it's always going to be a natural log of that absolute value, okay, of the part that was from the denominator here. Okay, so it looks okay so far, but in the end, all of a sudden we realize the t that we chose arbitrarily here could be any value. It's a variable now. So now in that way, so now let me get back on the graph. All right, so this is the part of our problem. This is the part of our 1 over x function where the interval is from -1 to 0. So 0 is here right at the y-axis tentatively. So we're trying to be from -1. We're trying to make that accumulation from -1 to 0. But sadly, again, the function is undefined, is discontinuous at x equals 0. So the idea I brought up earlier, you see, we're going from -1 to t. So we pick a t value anywhere between -1 and 0. So 0 is our upper end. T is an arbitrary value between. And so here is a definite interval for here between -1 and t. Just like what I wrote on the board right here. Okay? But this accumulation here represented by the blue area on the picture will never be the actual answer. Will never be the actual answer. It matters here, what matters here is that it depends on where we put the t. Because the closer we put the t, see now I'm using that term as well, the closer we put the t to that upper limit of our integral, then the more area, the more accumulation we are reaching. Okay, so the answer for the blue area, the amount of blue area here is keep changing. So we want to find out whether or not this area, this accumulated blue area will come to a final destination or not. Okay, and so, but then in that way, in the action where I'm showing on the computer screen right here, we are dragging that handle to make our t coming closer to 0. Meaning we're letting t getting closer to 0, but you can see earlier that it's getting close to 0 from the, from the left hand side, because our t value in the end right here is always on the left hand side of 0. All right, so does that ring a bell for anyone watching the video here? So that means now this work getting an arbitrary definite integral is not enough, but we need to create a limit work. We need to apply on top of that a limit operation, where now this time I'm allowing t to approach 0. Okay, 0 was tentatively that upper limit from the beginning right here. But now you saw earlier through the graph, we're approaching that from the left-hand side. So that's now how I put that negative super minus sign or superscript minus sign right there. And so now that means any work along this, any of the steps or any of the fundamental theorem of calculus steps right here, then I need to apply that limit work on top of that by letting t approaching 0. Letting t approaching 0. Okay, and that's the idea right here. And then whatever the answer will come out, it depends on how we calculate this limit. And so now specifically now just to focus on the limit work here. And I will ultimately make that connection from the work with that answer later. Okay, as once we formalize into the definition. But here with this limit now, well, natural log of -1, but -1 is already trapped in absolute value. So you can think of that as natural log of +1. It's 0. So that term is 0, nothing to worry about. So this natural log of t right here, but as t, you see, think about the consequence a little bit. T is getting closer to 0 from the left-hand side, and t will never be at 0. So that means t has to be always a value negative, but negative in absolute value will become positive again. So that's the same as, so this thing here is the same as the whole absolute value of t is getting close to 0, but from the right-hand side. It's all due to the fact that t, yes, coming close to 0 from the left-hand side, but absolute value is forcing it to become the positive side, so it's like it's coming from the other end. So just like that, logarithm, as a reminder, has a graph that looks like this. So now if we force everything on the right-hand side, to the positive side, and that means we're getting close to 0 from the right-hand side this time again. So the answer now comes out to be, see it, heading down that way. That's my arrow pointing. So now it's, as far as the limits problem, it's a minus infinity. Okay, it's a minus infinity. And so now we are ready to make the final definition right here. All right, and so now let me write down another definition. Okay, so clearly speaking, the two integrals I brought up earlier, they're all improper integrals. It's just not the one that we can do the fundamental theorem of calculus as usual. Okay, so now I'm going to say, let me mention the first form that I brought up, the improper integral. And now I'll just get straight into introducing the definition here, and then I will explain even more about that. Okay, so the improper integral in the form A, an integral from a to b on the function f of x, but it looks just so like an ordinary definite integral. So that improper integral on the interval from a to b. But now look closely at the way how I'm writing. The interval here is open-ended on a and closed-end on b right here. That means of course, allow me to skip some minor details right here. So all of the standard wording of these definitions are given in any standard calculus textbook. But here, this interval here being open-ended on the left end right here means that the function is discontinuous on that end. It's only defined anywhere inside of this interval, and then it's undefined right on x equals a right there. Okay, so then the integral, that's why I'm saying the improper integral on that interval. Okay, namely a to b on the function f of x. Now that integral here is now defined as, so I will get even more clear about this equal sign right here, but it's defined as it's defined to be, or the outcome of this, the numerical outcome of this integral right here is defined to be equal to the limits work on the integral that, so you have seen that earlier in the work. I created an arbitrary t value. Okay, so from t to b right here, we're creating this limits of an integral and then letting limits of t approach a from the from the right hand side. All right, so now we let the answer to this improper integral to equal the answer of this limit if the limit exists. Okay, if the limit exists as a finite value. All right, so that's form A right there. So this form right here came straight out from our demonstration example that I made earlier, from 0 to 1 on the 1 over x function right here. The interval the interval that f of x continuous, the interval where f of x was continuous on was only from 0, anywhere between 0 to 1. Okay, so that's interval. This interval here is half open right there. The left end is open, the right end is closed. All right, and so that's why I left this work here earlier without an answer, without an equal sign, because the limits here obviously did not come out to a finite value. And that's why now if we're looking more closely into the definition, we can only have a definite answer to this improper integral anytime we have a successful limit outcome of this, a successful numerical answer for this. Otherwise, and so in that case right here, let me continue with my definition right here. So, okay, the integral is said to be and you have seen that term when we were in the other half, in the earlier half of our discussion on the improper integral. This integral is said to be convergent. Okay. if the limit exists. And limit, I mean this limit right here. If that limit exists as a finite. Okay, and then it's said to be, and otherwise, meaning when the limit here fails to exist, either being an infinite limit or a non-existing limit, and that's what I mean by otherwise. And otherwise, divergent. All right. Okay, so that's the definition for how we can, so this definition here defines for us a way how we can handle this improper integral of this kind right here, where the lower end right here, the lower end of our integral is the discontinuity side right here, the discontinuous side. Okay, so the interval here from a to b, it has the low end is giving the discontinuity for the function f of x on the low end. Okay, and so similarly on that way, I'm going to step over to my other board. And so just like that, the improper integral that's in case b right here on the interval that from, now we have a closed end on a, the left end of the interval, but open end on b right here. That integral, namely that integral from a to b, but see, half open, closed on the left end and open on the right end. Okay, this integral is defined to be, okay, and you have seen that through the demonstration earlier, defined to be the answer to this limit from a to t. It's an arbitrary definite integral that we create with a t value anywhere less than b, but we're taking limits allowing t to approach b, okay, from the left hand side. And again, allow me to skip some other details right here, but I'll only focus on the main core definition right there, and those other details you can find in any of your standard calculus textbooks right there. So we define this integral, the answer to that integral, as the answer that comes out to this limit, but only if, the limits, and that limit, of course, if the limit exists as a finite value. Okay, and then in that case, if the limit exists as a finite value, the integral is said to be, again, the integral is said to be convergent. All right, said to be convergent if the limit exists as a finite value. All right. And otherwise, it is divergent. It's said to be divergent. All right, and so now you can pause the video at any point, write down take notes on the definition here, okay? And sadly, I'm going to have to very shortly here erase the definition and get to do some actual examples so that to demonstrate what what exactly all that definition here means. But in the end, generally speaking, bringing up the limits problem is the way how we let this work be. Okay, so we let the answer of this, we let the answer to any of these two forms of the improper integrals to start out by being a limit work, and then if that limit work comes out to be a numerical answer, which we haven't seen yet, okay, but we will see. But if this limit come out to be a numerical value, then we can say that this integral has a final answer numerical value equal to whatever came out from this. Otherwise, if this is giving us, as you have seen earlier, if this is giving us a non-existing limit or a value limits value other than infinity, other than a finite value, then we're going to say that the integral here is divergent. Okay? So now, I need to erase the board space here and come back to the two. It's not even example yet. It's not even our formal example yet, but I'm going to come back to the problem I've had earlier, the demonstration problem I pointed out earlier, and make a conclusion. Make a conclusion based on this definition I've given right here. Okay, but allow me to really erase the board here. All right, so these are the two forms of the improper integrals where we have discontinuity in either one of our two integral limits right there, either on the left limit or the right limit, or the upper limit or the lower limit. Okay, so back to that problem I brought up earlier. It was from 0 to 1. Clearly speaking, this is now an improper integral. We did all that limit work. Okay, so as a formally, see, that's why I did not write equal sign as first, because we don't know what that limit was. We don't know the final outcome of that limit was. So all I did was creating, for this problem right here, I was creating an arbitrary integral from t to 1. Okay, and I took the limits, letting t approaching 0 from the right hand side. Okay, and so 0 is this is A, and it's actually an open interval there, and B is closed. See, so or 0 to 1. I kept mentioning that too quite often enough, and then the function was 1 over x, and we proceeded our work, and we ended up with this limit turns out minus infinity, if I remember correctly. And so now, if we strictly base on the definition, I want to move cautiously with this with this type of improper integral right here. When this integral, when this limit runs into an infinite, now as long as your final limit is not a finite value, then that means we don't have equality here. Don't say it's equal or anything like that, but I'm going to say the conclusion here is this integral as a conclusion from 0 to 1, the improper integral 1 over x, okay, is now based on the definition, divergent. And that's all I can say. That's all I can say. Divergent. And we won't even attempt to find a numerical answer because there won't be any. Okay, so we don't even try to make equality. Even though quite a few textbooks, it is okay if any of my students to write this as equal that and then work your way through separately on that integral as well. But when it gets to this point, now remember when I was going over the infinite limits, it's mostly the similar idea right there. But throughout many of my examples, I also get the starting step by setting it equal tentatively. And then we separately branch out and work on the limits. But here I highly recommend my student not to write that equal sign because it will create a dangerous habit later on. Okay, and I don't want that to happen. And so here we have a problem, an improper integral of this kind given to us. Just get started by getting straight into this limit work without worrying about equal or not. And then we're going to work our steps out on the limits, so all that equality things happen. But then anytime we run into an answer that is not a finite value, then your conclusion for that beginning integral is simple. Your integral there is divergent. Either you have an infinite limit like this, or you have a non-existing limit. Okay? But now, other than that, if in some other case where gladly this limit here turns into a finite value, then we can say that this integral equal to this answer, equal to that whatever coming out answer, which is not this problem right here. Okay? So now, we are ready for some actual example. All right, and continuing from my last example in this lecture here, I'm going to call this now example 4 right here. Okay, and I'm going to be staying with the exact same style of wording right here. And let me introduce that style of wording again. So I want to determine, we want to determine or decide whether the given interval, the given integral and of course improper integral. So the given integral is either convergence or divergence. Okay, so that's the first thing to decide. And then if we know it's divergent or convergent, if it's convergent, all right, then we're going to go ahead and evaluate the integral. All right, so that's the main instruction of the entire problem. And then throughout this example 4 here, I'm going to introduce 2 different improper integrals, okay? And we're going to start calling that part A, B, and C, and D, and so on. Okay, and then depending on how many I have prepared so far for anyone watching the video here, then we're going to have just more experience and more experience. You don't have to watch through all problems, but it's highly recommended that the more you watch, the more you learn. Okay, so now let's look at part A. Okay, so for our problem here, I'm looking at how about an integral from 0 to 1 on the function 3 over x to the 5th. Okay, 3 over x to the 5th. Okay, and so again, right at first sight, any of these improper integrals is very dangerous in a sense that if we're just if we're just making judge right at only by first sight right here, then it looks so like a definite integral where you can just simply use the fundamental of that theorem of calculus to handle the problem. But nope, that plan is not going to work out, because see, now if we're looking a little closer, a little more closely, then the bottom end of this integral right here is that discontinuity points in this function right here. For this function, 3 over x to the 5th. 3 over x to the 5th does not have x equals 0 in its domain. Okay? And so now that rings a perfect bell for us that, hey, we have to do this problem. We have to do this problem where, as following. So I'm not going to say equal. Okay? That's the idea. But first thing in the first step into doing this, I am going to set up an arbitrary definite integral from t to 1, where my t is, of course, less than 1. Okay, the function is 3 over x to the 5th dx. But this is now a definite integral where we can use the fundamental theorem of calculus just fine. Okay, and then, but then on top of that, we have to produce the work here as we have to let t approach 0. See now 0, it's not just 0 because we do t, we don't always want t to go to 0. We want t to approach the bottom end of your original integral problem. That's the idea. So if it has a discontinuity point here at 2 right here, I mean at -1 right here, then you're gonna have to go t go to -1 from the right hand side. Okay. And so now, and I will bring up a different problem later on, of course. But so, you don't need to worry about the limits yet. The main problem to worry about is this problem right here, where we can now safely use the fundamental theorem of calculus on this integral. And so now, it says we can, and by the way, how about one more step right here to make it clear about what kind of function we have. We can rewrite our function as a 3 times x to the -5 power. And now the problem becomes really clear. And we're letting t approach 0 from the right-hand side, so we didn't even get anywhere further yet. So I'm just playing around with the algebra of our function. And so now with that function right here, then the answer to the antiderivative becomes clear. It becomes a -3/4, okay, and allow me to pick up a fast pace here on the antiderivative work. And it's x to the -4, okay. And then fundamental theorem of calculus say we will, in the next step, evaluate this from t to 1. Okay, but don't forget, we have to work this problem in the end as a limit problem where we're letting t approaching the low end of our original integral interval over here, but from the right hand side. That's why I'm putting that plus sign right there. Okay, and so now in that way, you can see that at this point, throughout all the steps we've been doing so far, the limit is only some reminder that's hanging there, so that you have to remember we apply the limit at the last step right there. So go ahead and do the usual fundamental theorem of calculus. So now it's minus 3/4 times 1 to the negative 4 power, which will eventually be altogether here is a negative 3/4. I'm going to subtract minus negative 3/4 with t to the negative 4 power. Okay, should have used square brackets here. All right, and then all together, all of these here, that term is a constant term. This term is a term in terms of t. So now we're clearly having an expression in terms of t. And so now it becomes clear that our problem is brought into a limit problem where we're letting t approaching 0. And remind yourself again, 0 is the low end from the original integral. Okay, the low end on the original integral interval. Okay. And so now I'm running short of space here, and of course that in the next step that will become a negative 3/4, and that's become a positive, so negative 3/4 plus the 3/4 t to the negative 4. I'm going to write all that in the next step right there. I mean in my other board. All right, so now in the next step, as I have already pointed out, and we're looking at a minus 3/4, okay, but plus a 3/4 times t to the negative 4. All right, and we're taking this limit as we're allowing t approaching 0 to the right hand. From the right hand side, approaching 0, but from the right hand side. Okay, and so now the rule for the limit law says that is a constant term, so we don't have to worry about that. It stays negative 3/4 after we're taking the limit. Okay, but this will be, you see, 3/4 times t to the negative 4 power is the same as, this is the same as 3/4 t to the 4th. That's how I'm seeing it algebraically. So that means as t is getting closer to 0 from the right hand side here, from the right hand side, then this overall fraction is going to grow up infinitely. And I mean positive infinite. And so again, save me from all that argument, save me from all that logical argument, because I've given all that detailed explanation back in my video lectures for Calculus 1, the differential calculus course right there. So here I can just assume anyone already had that background. So this right here give me a positive infinity. So in the end, the answer turns out to be, it has a limit. I still see this as having a limit. I'm a little bit unlike many math professors out there who just say this is immediately a non-existing limit. I see this as a limit. It's just not a finite value. Okay, but now here's the answer. As long as our overall limit here did not come out being a finite value, then now I'm going to say, unfortunately, as a conclusion, that's why I did not make any equal sign from 0 to 1. 0 to 1, and the function is 3 over x to the 5th. This improper integral is, and the answer here is divergence. And that's all we can say. And once we can conclude that the integral is divergent, there's no further need, there's no longer a need to find its numerical answer at all, because there won't be. It won't be. We won't be able to find it. Okay, that's what divergent means. It won't have a value for that, a finite value coming out for that. Okay, so the limit work is the biggest work, but the limit work once it's passed, and passing means that we get the final numerical outcome being finite limits, then we're going to say, hey, this answer equal to that, but otherwise we're going to say this work here is divergent. Okay, Let's do another one for you to build more experience in any of these problems. All right, so now part B of our example 4 right here. So what about we are looking at an integral from -2, okay, -2 to 14, okay, and then dx over 4th root of x plus 2. Okay, 4th root of x plus 2. Okay, and now I had a clarification further that to indicate. I had a short video to clarify that this is exactly the same. And I mean, I also expect any viewer who viewed this already understood what this is. But in case that you are not familiar, then this is the same as the function here is mainly 1 over 4th root of x plus 2. And I had that in a clarification video earlier from this point. And then with the dx here, so our function is this function. Okay? But now apparently with this function of ours, you can see again that it's very similar to the earlier one. It's on the interval of integration here is -2 is the low, 14 is the high. Okay? Is the function continuous on 14? Yes, it is. So it's a closed interval here. But is this continuous? I mean, is this function continuous at the lower end? Sadly, it's not. So I leave that as an open end there on the left end. So that's how I'm seeing it. It's just like the earlier problem. The lower limits of the integral is the open end on this interval right there, or it's the discontinuity end right there. That end with the discontinuity. Okay, and so now to find an answer, to look for an answer of this, we start out by doing the limit. So I don't rushly set equal sign yet. I'm just saying we're going to produce an integral that goes from an arbitrary t value to 14. Okay, and then our function here is 1 over 4th root of x plus 2. Okay, but then we need to take the limits as t. See, in many examples, including the demonstration problem, I've been using 0 as the lower limit. So it might make people think that it's always go to 0, but here it's going to recall the rule of thumb is to go to the lower limit. Okay, lower limit here, but from the right hand side. From the right hand side. So just look at the interval itself right here. See, -2 is here, the low limit 4 is here. Okay, we pick a t, we put an arbitrary t here. So tentatively we're working on this. So this integral from t to 4 is a usual integral in a sense that it's just any of those usual definite integral, but then we're going to let t come closer to -2. And that's why it's t getting closer to -2, but from the right hand side. Okay, and so now once we have it all clear and nailed down with that, now I'm gonna proceed as the usual fundamental theorem of calculus. Okay, that I'm seeing that it's good. I'm using a little bit of a substitution. So how about I'm gonna let you, and I'm gonna quickly erase this scratch work right here with using a u substitution. I'm gonna let u equals x plus 2. So that means du. Okay, du dx will equals 1, and that leads to du equals dx. And then when u equals, and then that also means the lower limits equivalent to the original one now is going to be 0. I mean, sorry, it's not the right one. It's this one right here. The lower limit is t plus 2, and the upper limit u2 is 14 plus 2, which is 16. So now my new integral would be as following. We're looking at an integral from t plus 2, the lower limit, and then 16 as the upper limit. 1 over, I made a substitution for x plus 2, so my integral become 4th root of u, which is a lot simpler. And dx is substituted by du right here. And once again, if you're unsure how I'm making all of these logical arguments, I highly recommend watch my video lecture on how I carry out the substitution method like that. Okay, and so now, in the end, we treat this as a problem letting t approach -2 from the right-hand side. But now, surprisingly, this integral is a lot simpler where we can handle that using the fundamental theorem of calculus before we applied the limits work right here. All right, so now I'm seeing this problem here. Let me write this a little closer so I can make more space for myself. So I'm seeing this problem here as it's an integral problem again of u to the negative 1/4 power. Okay, and we're integrating from t plus 2 to 16. And then yes, at the end, once we're done with that, we're taking limits, allowing t coming close to -2 from the right-hand side. Okay, and so now that means, so now we are really ready for the antiderivative work right here. U to the, and see the whole point, you gotta view my, see how I explain about the substitution method. It's a fascinating work out there. But so here we completely moving on in terms of u variable now. So u here to the 4th power, to the negative 1/4 power, so taking the antiderivative, it gives me 4/3 u to the 3/4 power positive. Okay, and then yes, we are going to evaluate this from bottom end t plus 2, upper end 16. And then yes, we need to, in the end, we need to find whatever that the limit of this overall expression as we're letting t coming close to -2 from the right-hand side. Okay, so now further with the fundamental theorem of calculus, okay, I'm doing 4/3 times 16 to the 3/4 power, and then I'm going to subtract, okay, and then now I'm going to subtract 4/3 okay, 4/3 t plus 2, because the lower end of the integral here is a t plus 2 to the 3/4 power. All right, and that's what I'm doing here. So in the next step, I'm going to go ahead and evaluate this. So 16 to the 1/4 power is a 2, but then raised to the 3rd power is going to be an 8. So 16 to the 3/4 power is an 8, but 8 times 4/3 is going to be 32/3. So I have 32/3 in my next step on the other board, and then this will remain the same. We don't need to FOIL out, because it's impossible to FOIL out this thing right here. But we can leave that either as a root form or as a form like this. We're going to be just fine. But now we can realize that it's completely an expression in terms of t. Now it makes perfect sense that we can take the limits of t by letting t go to -2 from the right-hand side. So let's see what it turns out to be. Okay. So on this board of mine, from the previous step, I'm looking at, okay, so it's a limit problem where we're letting t approaching -2 from the right-hand side, and here it's an 8/3 minus, and it's not 8/3, it's 32/3. 32/3 minus 4/3 times t plus 2 to the 3/4 power. All right, so now on this function, it is clear that as t is getting close and limit laws apply here, I see a t plus 2 and then inside a power. So limit laws is completely applicable here, all the limit laws that we've learned. And limit laws on a constant here say it remains a constant, 32/3. The limit laws say we can tear the problem into 2 separate limits. Okay, so that means we're going to go 32/3, subtract limits of as t going to -2 from the right-hand side on this function. And we can also bring the 4/3 in front. I should have also combined those. Okay, 4/3 times limits of t getting close to -2. Okay, and then in the end, I highly recommend you review your calculus 1 understanding. So now all that here is gonna be, now it gives me a minus 2 plus 2. It's not really we're plugging in, but limit laws allows us, right, to do the work similar like that. And so now in the end, all that term here becomes a 0. So we have left behind a 32 over thirds minus 0. So my final limit here is a finite value. We have a finite value limit being for this limit, it's being a 32 over 3. It's a finite value. Sweet. Okay, so what does that mean for us? What does that mean? That limit's there having a finite value. So what does that mean for this integral? Because we were starting out doing an integral problem, and then all of a sudden at that magical point we completely turn our focus to over working as a limit problem. So more experience for anyone who got out of calculus 1, and here you go. You see more problems on limit work. Okay, you will never get away from limit work once you've learned it. You will never get away from anything once you've learned it. Okay, but so that's integral right here. Now the limits from the other board you have seen turns out to be a finite value. That means this integral here is a convergent one. So now I'm going to get back to that board to make the conclusion. So that means my huge arrow here means we can make a conclusion now. That's the integral from minus 2 to 14, okay, on this function 1 over 4th root of x plus 2. This integral is convergent. That's how, now I got to emphasize again, the instruction of this problem, which is a quite standard kind of problem, very standard and popular kind of problem among all problems on the improper integrals out there, that we have to first determine if our integral given here is a convergent one or a divergent one first. And once we know if it's convergent, so this is the step after once we know it's a convergent one, then we're going to evaluate the numerical value of the integral. Okay? And so now at this point we have made that conclusion that, hey, this improper integral is convergent. So now I can legally say, another arrow right here, another implication. This integral from minus 2 to 14, okay, of 1 over 4th root of x plus 2, this integral has numerical value equal 32 over 3. All right, and now I can put all this in a box right there, or you can just simply put that answer 32 over 3 in a box. It's a lot of process, but that's how it's done, like that. Now, again, as I've mentioned, many textbooks and many other professors will commonly allow students to write this to equal the limits and then start working out with the limits. That is okay too, but it's just in my own experience, I found it created a dangerous the habit. And so I decided to go slightly different. I decided just, once you had the problem given, just leave it there. We're going to purposely produce a limit problem and spend the entire time working on the limits problem. And then only when we arrive at a final definite answer of a finite outcome, a finite numerical value for this limits, then you can say the integral equal a value. Otherwise, you just say the integral is a divergent one. Okay, so I highly recommend going in that path here. It will reduce some of the headaches later on, where you have to kind of trap yourself in a lot of other logical reasoning, because there are still a lot more details about these improper integrals out there outside of what we learn here at the calculus level. Okay, so now that's how we're doing part B of the example. So start keeping in mind, and it's still the same kind of problem ever since example 1, that we're still working on those improper integrals with the infinite interval. So here we're looking at the different kinds of interval. The interval that contains a discontinuity either on the left or the right end. But in the end, we always have to first determine if the integral is convergent or divergent. And once we knew it's convergent, then we're going to go ahead and find what its numerical outcome is, which is namely the answer that came out from the limits. Okay, so now let's look at part C of the example. All right, so in my part C of the example, now here we go. It's that problem I brought up earlier on when I was introducing it, but I was only beating around the bush there, and now we're going to really get into it. From 0 to pi over 2, and our function here is tangent of x. All right, so we want to look at that integral problem. The function here is tangent of x. The function is defined at 0, the lower end of our integral interval, but it has a discontinuity on the upper end of our integral interval. Okay, so in that way, now clearly it's but this time I want for you to understand, if we refer this back to the definition I introduced earlier, then this is form B right here among that definition. Okay, so this is how I see it. Tangent is continuous at 0. So in this interval from 0 to pi over 2, it's closed end on 0. But then it's going to be open end on the pi over 2. Because apparently speaking, I mean, tangent is undefined at pi over 2. Okay, that's how it happens. And so that's why I have to leave it an open interval. But now then, from that, once we realize that, then we can do the following. I am going to make like I said, I'm not going to make any equality or anything like that. I'm just writing, I'm going to produce separately an integral, a definite integral from 0 to an arbitrary t this time. So t this time, that arbitrary t, to make our definite integral, is going to be the upper limits this time. Okay, from 0 to t. And then the function here is tangent of x. And then, yes, we do need to let t approach pi over 2 from the, but this time from the left-hand side. All right, it's pi over 2 from the left-hand side. My pencil stroke is making it a little bit unclear to see from the left-hand side. But see, I'm not saying that this is equal to that yet. I don't want to say that right at this point. I'm just saying out of nowhere, and that's the way it is. We define that work by first do this. The work of doing this is first done by producing that limit. Okay, and we're not sure if it's equal in the sense that we haven't found that limit value yet. So I wouldn't say equal. We're gonna just start working on a limits problem. Okay, and once we've had some answer on that limits problem, we're gonna start making conclusion about this. So now I can apparently see that tangent is a sine over cosine. So we can go a little bit of, well, maybe for anyone to also re-enhance your understanding, and I can write that as a sine over cosine for tangent. Everything else in the problem remains exactly the same. And so here I'm going with substitution again. So I'm going to let u equal cosine of x. Okay, I'm letting u equal cosine of x. And so that means du dx is going to be minus sine of x. And in that case right here, that means du divided by minus sine of x, which equals dx. So I found a substitution for dx later on. And so that's the whole point of doing substitution. Cosine in the next step will become u. And then and here I forgot my limits right here. Okay, and so from that point, if u equals cosine of t, then the lower end here, u1, in respect to the new variable, u1 is going to be cosine of 0, which is 1. Okay, and u2 will be cosine of t. Okay, cosine of t. So that means, and shortly I will erase this extra substitution work with that to only focus on the integral. So here, our integral turns into the following. We're looking at sine of x. Well, that did not get a substitution. Leave it there over u. And then the dx here is substituted by du over negative sine of x. Du over minus sine of x. Okay. And then I'm integrating from 1 to cosine of t right here. Okay, cosine of t, and then take limits allowing t to approach pi over 2 from the left hand side. Okay, All right, so that's what it is. So now I am going to, so I'm going to cancel out the sign of x, and there's the negative sign right here. I'm going to bring it out front, making it so it's a limits problem. Okay, as t getting close to pi over 2 from the left-hand side, but this is now a minus, and we go from 1 to cosine of t. Okay, and our function now is simply 1 over u with the du. All right, and so that's making it a lot simpler. So in my next step, we're looking at natural log of u in absolute value, and then I'm according to the fundamental theorem of calculus, and then we're going to go from 1 to cosine of t for that. But then don't forget, we need to take, and then actually I forgot that minus sign, so now it's here. Okay, and then now it's t approaching, we're letting t approaching pi over 2 from the left-hand side. Okay, t approaching pi over 2 from the left-hand side. All right, so now I'm going to navigate to my other board right there. All right, so still, we have not started on the limits part of the work yet, so let's just leave it hanging here. Okay, so now I'm looking at, after the fundamental theorem of calculus, then we're going to evaluate our antiderivative minus natural log of u, but now u is substituted by cosine of t. So cosine of t is here, okay, minus natural log of, in absolute value, cosine of t. And then we're going to subtract, okay, and then there's a minus natural log of 1 in absolute value. All right, and that here is essentially 0. Anyone should know this at this point in watching the video here. And so now we're mainly looking at limits problem, and it makes perfect sense at this point that since our expression here after the fundamental theorem of calculus turns out to be an expression in terms of t, so it makes sense that now this problem is a function of t, and we're taking limits for letting t coming to a limit point. Okay, and so now minus natural log of cosine of t. Okay, and so think of the pi over 2 units, pi over 2 points on the unit circle over here. Let me remind trigonometry a little bit. Okay, pi over 2 is here, but coming to t, so t is the amount of angle in that row over here. But so t getting to pi over 2, but from the left-hand side, that means that we are going in the counterclockwise direction. So as we're getting close to, as we're going that way and getting close to pi over 2 from the left-hand side, that means on a unit circle we're going that counter direction way right there. Then cosine was 1 when t equals 0, and then cosine keep getting smaller but in the positive value. So cosine still positive value until it hits 0 here when we get to pi over 2. And so that means this part right here, this cosine of t will get to 0, but from the right-hand side right there. Okay, from anywhere larger than 0, and we keep shrinking down to 0. So now that means our natural log here, that means the natural log. And so now consequently the natural log of something that goes to, so this go to 0 from the right-hand side, but so overall the logarithm, the arguments of the logarithm, so on this axis is the cosine of t on this axis, but if cosine of t getting close to 0, then logarithm of cosine of t, okay, this function here is logarithm, let's say logarithm on the cosine of t. Okay, if logarithm of cosine of t, so if cosine of t is getting close here, and cosine of t is just a variable, Okay, so don't worry about it. It's looking a little fancy, unlike the usual logarithm you're seeing, but now just think about it as a one expression, as one variable, if the whole cosine of t going to 0 from the right-hand side, and so your logarithm of cosine of t has to keep falling down to the negative infinity. But now with that negative here, then it's altogether going to be an infinite answer, a positive infinity for this limit. Okay, so what does that mean for this integral? That means, unfortunately, the only thing we can say now is that the integral from 0 to pi over 2 on tangent of x, this integral is a divergent. Okay, that's all we can say. This integral is divergent. Okay, and so now, and once we made that conclusion that it's divergent, there's no need to find the actual final answer anymore, the actual final numerical answer. Okay, and so that's how we handle this problem in part C. And now let's look at another problem in this example. All right, so the next one here I have in this example 4. Let's look at part D right here. Okay, so how about the integral we have here is an integral from 1 to 2, okay, of the function 1 over cube roots of x minus 2, okay, with a dx. All right, and so now again, just quick double check right here. You can see that this function, I mean the integral itself, again, at first sight, it looks very dangerous, because if we're only judging by first sight, then we mistakenly will think of this as any of the usual definite integral, which is not a good thing at all, because this function here is indeed having a discontinuity at x equals 2 right here. So low n is fine. We can plug x equals 1 into the function, so that's why I can include 1 in our interval. Okay, it's a closed n on 1, but when it's on 2 right here, we can't include 2 in the interval, because it's not in the domain of this function right here. So the interval here is an half open interval from 1 to 2 right here, and open parentheses on that right end. Okay, so now in that way, again, we realize that form B, according to that definition I just introduced earlier in this part of the video lecture. And so now I'm seeing that the start here, I'm going to set up an integral from 1 to arbitrary t value. It's now a definite integral, really a definite integral. 1 over cube roots of x minus 2. All right, and then we're letting this limit, taking t to 2 this time from the left hand side. Okay, so the rule of thumb here this time, ever since part C and D here, the rule of thumb here is we're going to let t getting closer to the upper limits, but from the left hand side. Because think about it, the interval is here, left end is fine, but the high end is not fine. The high end has problem right here. That's why we're leaving it open. But we're creating a t is somewhere to the left of B. That's why now as we are approaching, as we're moving that t closer to the upper end, it has to go to, so the upper end here is, the left end is 1, the upper end is 2, so we're letting t closer to 2 in this problem, to 2, but from the left hand side. That's why we have this. Okay, and so now let's go ahead and continue to work right here. So I am going to use a little u substitution. So u equals x minus 2, and that means du dx equals 1, or it leads to du equals dx. And then in the meanwhile, it's a definite integral tentatively for this problem. So we're going to go ahead and substitute the value here and the value there into our substitution for u to get low n in terms of the new variable u, and a high n in terms of the new variable u right here. So u1, the low n, is -1, because 1 substituted for x, so 1 minus 2 is -1. u2 is going to be t substituted in the expression of the substitution here, so t minus 2. All right, so our integral becomes the following. We have an integral from -1 to t minus 2. The function now is a 1 over cube root of u, because all that x minus 2 was substituted away by u right there. Dx also gets a substitution, so that substitution is here, so we can substitute dx by du. So I'm looking at that entirely brand new integral. Okay, and now allow me to erase the substitution work right here. And so we can, this is, yes, still in the end a limit problem. All right, so now what I'm seeing here algebraically, it's u to the negative 1/3 power, u to the negative 1/3 power. Okay, and we are integrating that from -1 to t minus 2. Okay, and we're going to let t approach 2 from the left hand side. Okay, and so now that means in my next step I can go ahead and apply the fundamental theorem of calculus. So now it's just a simple power rule over here. So the power rule says we're going to end up with the 2 to the 2/3 power, but multiply by 3/2 in front. Okay, and now that's the antiderivative ready for evaluating at -1 and t minus 2 in the next step. But this problem, remind yourself, will be a limits problem at the very last stage of the problem. Okay, and so now I'm going to look at, so substituting t minus 2 into the expression, I'm looking at 3/2 t minus 2 to the 2/3 power, okay, and then minus, now -1, I mean it's still a 3/2 right here, but -1 to the 2/3 power, okay, and then here I'm taking the limits, allowing t approach 2 from the left hand side, okay, and so now -1, taking the 1/3 power is going to be a -1 again, but square is going to make it positive. So positive 1 times a negative 3/2. So I'm going to expect a minus 3/2 overall in this term here, but it's a constant term. But I will use that for my next step on the other board. And then here, there's no reason to FOIL it out or anything like that. We can't FOIL out things inside of square roots, right? And so now, on this board of mine, okay, so we're still looking at the limits problem, and we haven't done any limits work yet. Okay, now the problem just reduces down to, it's a 3/2 times t minus 2 in quantity 2/3 power, and then we're subtracting 3/2. And now apparently it is a limits problem in terms of t, of a function in terms of t completely. All right, and so now here's how I'm seeing it. So limit law is applied, and then that term here will go to 0, and this term here remains 3/2. So in overall, it's a 0 minus 3/2. So my answer finally is a finite value minus 3/2 like that. All right, so what does that mean for our integral? So our integral at start was an integral from 1 to 2 on this function, 1 over cube root of x minus 2. Okay, so this integral here now we can make a conclusion because the limits work. See, I did not make any equality. I did not equate anything at all. I did not equate this with this in the beginning. All I just say is, from knowing that we have an improper integral of this kind, I'm going to start out by producing a limits problem. And then now we work our way through with that limits problem. And then now as soon as we reach to the limits here as having a finite numerical outcome at the end right here, now I can say that this integral, improper integral, is convergent. Okay, it's convergent. And now being convergent, now we can proceed to the next step, because the instruction of the problem says first we have to determine if it's convergent or divergent. Now we know it's convergent. Then the next step, we're going to move on and evaluate the actual integral meaning we're going to find the actual numerical value. So now the numerical value is going to be clear. This integral does have a numerical value. The numerical final value, that is equal to, minus 3/2. And because of this logic right here, that is the reason why many textbooks, including the definition was saying this equal to the limits. Okay, but that's really, that equality in the definition just means we set out our work. It defines a way of doing this. We're doing this here by first starting out with a limit problem. And only when we arrive at an answer, then that beginning improper integral equals to the final numerical answer of that limit we're having right there. Okay.